Let's take another look at the linearization to a function near some certain point. The idea is that we want to use the derivative of the function at a certain point to get a good approximation for what the function looks like. We call this a linearization because what we're going to use is a linear function to approximate f. We love linear functions because these are the most simple of functions and the easiest to work with. Let's start out by looking at what's happening in general to see if we can understand what's going on. Okay, here I have the graph of some function, and I know a little bit of information about the function, but not too much. I know that it has these kind of wiggles in it, but that's about all. I'm interested in the function at this point because someone somewhere has told me that that's an interesting point to look at the function. And so we're going to call this point x equals a. All right. So in order to figure out what's going on with this function, what I want to do is I want to say this function looks kind of like a straight line as long as I zoom in enough near this value a. So let's go ahead and zoom in a little around the value a. So here's a zoomed in graph of my function, and this is going to be x equals a. And you can see that if I draw the tangent line to the curve at this point, since I've zoomed in so much, the tangent line is pretty close to what the actual curve looks like. So if I want to move over a little bit, say over here to x equals a plus h, and figure out what the actual function value is, that's this sort of purple color, whatever the y value is in this case, I could instead look at the line and figure out what the value of the blue curve is at this point, because the blue dot and the purple dot are pretty close together. So the idea is, as long as I've zoomed in enough, that is, as long as my h is small enough, I'm near enough to the point A, I can say, well, if I can figure out what the value is on this line, and the lines are pretty easy to work with, then I can figure out what the value of the function should be close to. So I'm going to approximate the function value by using this line. This is called linearization. All right, so how am I going to approximate the value of the function? Well, there's two different ways that I could think of to look at this. The first is that I could use the equation of the line. This is some line. So it's y equals mx plus b for some m and b. Well, I know the slope of the line because I know that it's the tangent to the curve f at the point A. So the slope of the line is f prime at A. I also know the value of some point on the curve as well because I have this point A and the tangent line actually touches the curve there. So I have some point on the line. That would be x equals a and whatever the function value is at A. So I can use this information to solve for b. And then, once I know the equation of this line, I can plug in this other x value, x equals a plus h, and figure out what the function value should approximately be. All right, well, I'm looking at the line y equals mx plus b, and I've already said that I know the slope of the line, that's f prime at a, and I know a point on the line. The x coordinate was a, and the y coordinate was f of a. And so what I want to do is solve for this b. All right, well, then I just subtract this thing from both sides, and I end up with f of a minus f prime of a times a. This is these parentheses for evaluating the function, and this parentheses for multiplication, and this is equal to b. So the tangent line is y equals, well, my slope, that's f prime at a, times x, whatever my variable is, plus this b that I just found. We'll put it in big brackets. F of a minus f prime of a at times a. Now remember that what we're trying to do is figure out what the value is on the blue line, the y value on the blue line, when x is moved over just a little bit from a. So we have this picture, here I am on this line, y equals mx plus b. I found the m, I found the b, and now what I want to do is plug in x equals a plus h and figure out what the y value of this point should be. It should be pretty close to the purple point. All right, so now I plug in x equals a plus h, and then we'll simplify. So I have y equals f prime of a times a plus h, that's the x value that I'm plugging in, plus all this other stuff, f of a minus f prime at a times the value a. Let's simplify. So I have f prime at a times the value a plus distributing f prime at a times h plus f of a minus f prime at a times a. Well, here's f prime at a times a, and here's f prime at a times a, so these cancel. And what I'm left with is that the y value that I'm interested in is f prime at a times h plus f at a. So this says that if I move over just a little bit, however much this h is giving me, then the value that I expect the function to be should be approximately this thing here. So, in other words, if a is some value, maybe 5, and h is maybe 0.01, then f at a plus h is f of 5.01 is approximately equal to, well, f prime at 5 times this h, 0.01, plus f at 5. So this is approximation to the function f at 5.01 using this information from the derivative. So that's one way to look at what we're doing. Another way is to use the definition of the derivative. We're taking a limit, right? So f prime at, maybe we'll say x, is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So if I remove this limit and just focus on h being reasonably close to this x that I'm interested in, right? And now I'm worried about some particular point a, so I can change this to f prime at a. So f prime at a is approximately, as long as h is small enough, f of a plus h minus f at a all over this h. All right, but what I want to do is actually figure out what is f of a plus h. That was the thing we were interested in just a moment ago, right? F at a plus h. So I can essentially just solve using this approximately equal to for f of a plus h. So the first thing I do is multiply both sides by h. It's not 0, so because I'm taking this limit where h is near 0 but not actually equal to it. So I have f prime at a times h is approximately f of a plus h minus f of a. And so then adding this f of a to both sides, I get f prime at a times h plus f of a is approximately equal to f of a plus h. So we got exactly the same approximation for f at a plus h, except this time we used the definition of the derivative. So all of this is pretty theoretical, but the idea that I want you to take away from this video is that what we're really doing here is using this line, the blue line in this case, to approximate the value of the function. Now that we've seen how the general theory should work out, let's look at a specific example. Here's an example. We want to use two different methods to approximate f over g at 5.999 given the following data. So we get the value of f at 6, the value of g at 6, the value of the derivative of f at 6, and the value of the derivative of g at 6. So the first thing that we want to do is make sure we understand the notation. So f over g at 5.999 means f at 5.999 divided by g at 5.999. So we want to approximate this using two different methods, and we want to use the linearization because that's the topic that we're focused on right now. So method number one is to approximate F and G, then divide. So step one is to approximate F and G at 5.999. So in this case, we have our A, the nearby value where we know a whole bunch of things, that's 6, and our H, the value we move away from that value, is negative 0.001. So we remember that we are looking at F and G at some value, and we want to move away some point, some amount, and we want to use this tangent line data that we know. All right, so we know that the linearization is given by this formula. F of A plus H is approximately F prime at A times H plus F at A. All right, well, F at A plus H in this case is F of 5.999, so that's approximately F prime at 6 times our H, which is negative 0.001, plus our F value at 6. All right, well, we know F prime at 6 and F of 6 from the chart, so we have F prime at 6 is negative 2 times negative 0.001, and then F of 6 is 7.8, so plugging this in the calculator, we get that F of 5.999 is approximately 7.802. So it's not exactly the value, but the value that we would get if the function moved along at a straight line, which is not such an unreasonable assumption since we're so close to the value 6. All right, we can do the same thing with our function g. G of 5.999 is approximately g prime at 6 times our h, which is 0.001, plus g at 6. Well, okay, so we know g prime of 6 and g of 6 from the chart. So g prime at 6 is 8 times negative 0.001, and then g of 6 is negative 3.2. So again, plugging this in the calculator, we get that g at 5.999 is approximately negative 3.208. All right, so then in order to find the actual value, step 2 is to divide. So then f over g at 5.999 is f at 5.999 over g at 5.999, which we've just approximated. We got 7.802 for the f, we got negative 3.208 for the g, and so then if we put this in our calculator, we get approximately negative 2.432045 or so. So this has been a really good practice using the linearization of both f and g, but we want to do this in another method using another one of our tools from this week, and that's going to be the quotient rule. So let's go ahead and use the quotient rule. So method number 2 is the quotient rule to find the derivative of f over g at 6. So again, we want to talk about some notation for this. So the derivative of the function f over g at 6 is either, well, we can take d dx of f over g of x, right? So this is the derivative notation. This is the function, even though it looks kind of strange. This f over g is the function. We could call it h if we wanted to. And then we put a vertical bar here to denote the fact that we want to evaluate this. And then a little subscript, x equals 6. So this means take the derivative of this function and evaluate it at x equals 6. The other notation that we'll use is just to say f over g prime at 6. So the second notation is the one that I'll prefer for this example, but you'll see this other notation around as well. All right, so by the quotient rule, we know that f over g prime at 6 is equal to, well, g at 6 times f prime at 6 minus f at 6 times g prime at 6 all over g of 6 squared. Again, we have these values from the table, so let's go ahead and plug those in. So f over g prime at 6 is equal to, well, g of 6 is equal to negative 3.2, and f prime at 6 is equal to negative 2, minus f at 6 is 7.8, and g prime at 6 is equal to 8, and then g at 6 is negative 3.2. So we square this guy, and we get that the derivative, f over g prime at 6, is equal to negative 5.46875. So then step 2 here is to use the linearization of f over g. So f over g is just another function, and we're interested in f over g at 5.999. So this is approximately equal to, well, we use the same formula that we've been using, f over g prime at 6 times our h, which is negative 0.001, plus f over g at 6. Right? We just found the derivative of f over g at 6. We know our h, and we can find f over g at 6 by evaluating f at 6 and g at 6. So this thing is approximately equal to negative 5.46875 times our h, negative 0.001, plus f at 6 over g at 6. So we're getting negative 5.46875 times negative 0.001, plus, well, f at 6 is 7.8, and g at 6 is negative 3.2. And so plugging this in, we see that f over g at 5.999 is approximately equal to negative 2.43203125. So it's a whole lot of decimal places, but we put this here so that we can compare it with what we got from method number 1. So in method number 1, we got, let's see, negative 2.432045, which is pretty stinking close to this approximation. Why are they different? Well, because we're actually approximating different things in the two different methods. One, we're approximating f and g separately and using that. And in the second one, we're actually looking at the function f over g as a whole, using the linearization of that function and using that to approximate this function. So this has been a really great practice with both the linearization that we talked about in the first part of the video, as well as the quotient rule that we've learned this week. So there are some practice problems just like this on Mooculus, so go ahead and try those out. If you have questions, feel free to post them on the forum.